Let's break down the architecture of embedded systems in a way that's clear and easy to grasp. Embedded system architecture is all about the structure and organization of hardware and software and devices built for specific tasks. Unlike regular computers that can do many things, embedded systems focus on efficiency, reliability, and performance for one-purpose applications. You'll find them everywhere, from cars and consumer electronics to industrial equipment and medical devices. Let's start with the hardware components. At the heart of every embedded system is the processor, often a microcontroller. Microcontrollers are popular because they integrate many features at a low cost and efficiently execute instructions and control system operations. Memory is crucial too. Embedded systems use ROM or flash for long-term storage of firmware and instructions, and RAM for temporary tasks while the system operates. Input and output interfaces let the system interact with its environment through sensors, actuators, displays, and communication ports. Power management plays a big role in making sure devices run efficiently, especially when they rely on batteries. Systems also include timers and clocks to keep everything synchronized and on schedule. Shifting to software, firmware forms the core, the instructions stored in memory that make the hardware work. Device drivers allow the hardware to talk to higher-level software and your applications. Not every embedded system uses an operating system, but complex ones might include a real-time operating system, RTOS, to handle multitasking, scheduling, and resource sharing. Finally, application software puts all these pieces together to deliver the system's main function. Now let's look at common architectural patterns. Two primary structures are used in embedded systems: Harvard and von Neumann architectures. Harvard architecture has separate memory spaces for instructions and data, so the system can access both at the same time for greater speed. In contrast, the von Neumann approach uses a single memory for instructions and data, making it simpler but with potential speed bottlenecks. The architecture is layered for clarity and modularity. At the base is the hardware layer: CPUs, memory, input-output ports, timers, and power management. Next comes device drivers, connecting hardware to the operating system or applications. The operating system layer manages software tasks and resources, when present. Middleware can provide security and communication support. Finally, the application layer delivers the logic for the device's purpose.